Okay, so first one, they say, is there a relationship between the gestational period, time from conception to birth of an animal and its average lifespan? Okay, the figure shows a scatter plot of the gestational period and average lifespan for 43 species of animals. Okay, so part A, so actually let's just see this. This is gestation in days, and then this is the lifespan of the animal. Okay. So point A is the describe the relationship shown in the scatter plot. Okay. Okay, so whenever they say describe the relationship, that phrase, they mean do duffs. You don't have to go in that order, but so duffs is direction, so positive, negative, or neither. U is unusual features, and right now that's just clusters of points. Maybe there's kind of separate clusters. If there's all one cluster, that's not really a cluster. That's just all the points are together. But if there was like a cluster here and a cluster here, kind of separated, then you'd mention that. F is form. So for us right now, you could say linear or non-linear. Sometimes you could say a curve pattern. That's just the form of what the maybe least squares regression equation would be. And then S is strength, weak, moderate, strong, and then you can all talk about, very strong, very weak, moderately strong, moderately weak, or just moderate. Moderate would be just in the middle. Okay, so let's do that. So I would say with this one, definitely it's positive because this data is just kind of generally going positive. It looks a little curved here, but positive kind of in this general direction. I would say it's moderate. It's definitely not strong because at least as far as a linear relationship, because it's kind of curved. It starts out, if these points weren't here, it would be pretty strong, and a curve would be there. The least squares regression line would go through here if these points didn't exist. But I think these points are going to kind of drag it like this way, maybe. Be something like that. Okay, so that's just a moderate. So let's start writing this. So this is moderate. So not weak, not strong, just moderate. Definitely positive, no question. And we'll say linear. It's a little questionable, but and then we'll just say between whatever the variables are. Between gestation and lifespan. Okay, and so here and then unusual features. So definitely it looks like we'll say there seems to be three outliers. Okay, these two are, we could call just generally influential points. Really all three of these are influential points, but especially A would be more of an influential point. Actually, B, sorry, these two won't be so influential, even though they're kind of outliers, because they don't have, they have a pretty big X value, so they will be influential. But this would be like A would be a more influential point, it goes above or below on the, actually let's draw that. Okay, so let's say looks like A might be right through like the line of like what the mean of X would be, the X's. Okay, and then the mean of Y's, the Y's might be somewhere like right here, maybe 12 or so. Okay, which would make the line of best fit. Line of best fit, the least squares regression line has to pass through the intersection of these. And actually the X mean might be a little bit over to the right because of these 2 points. These 2 points have big X values and big Y values, so actually that might drag both up some, but we're just kind of roughly looking at this. Okay, so maybe it goes through this point, so maybe it would be something like this to go through those points. So that would be like this would be like whoops. Here, that might be the least squares regression line. Okay, so we'll talk about point B and point A, how they affect it in the next parts. Okay, we'll leave it at that for now. Okay, part B. So they say point A is a hippopotamus. What effect does this point have on the correlation, the equation of the least squares regression line, and the standard deviation of the residuals? Okay, for the correlation, so it'll definitely have a big effect on the correlation because the correlation is affected by points that have a big residual. So the residual for A would be, this distance. In general, a residual is, if you're looking at a scatter plot, is the distance from the point to the least squares regression line. So this definitely has the largest residual out of any point. This is the largest distance, vertical distance to the least squares regression line. So that's going to affect the correlation a lot. So the correlation will be greatly affected. Okay, and they talk about the equation of least squares regression line. So the equation, point B, the slope will decrease. Okay, and that's because that's because this point A, oh no, sorry, what am I doing, sorry, the slope will stay the same because this point here, this point A, since it's on the line for the X mean, this vertical line, it'll just draw up this line a bit. So this line will just this whole thing will come up and it'll just be a parallel line. The y-intercept will increase slightly and the slope will stay the same. Slope will stay the same. Y-intercept will increase slightly. Okay, so that's kind of talking about when they talk about the least squares regression line and then the standard deviation of the residuals. So definitely will increase because, this point A has by far the greatest residual compared to all these different points, right? Just pick a point. That residual is pretty small. That residual is pretty small. That one's kind of big, but A has the biggest residual of all of them. And so, if you think about all these little standard deviations are just or all these little residuals are just numbers. And when you have a list of numbers and you add a big number to that, then the standard deviation increases. So standard deviation will increase. And standard deviation, I should put of the residuals. Let me fix that. Part C. Okay, so point B here is roughly on this line. This line might be slightly different. I'm just estimating. So, but let's kind of answer the question, assuming that this is the line. This estimation is correct, but we'll see. So point B is the Asian elephant. What effect does the point have on the correlation, equation of least squares regression line, and the standard deviation of the residual? So same question as before, but dealing with point B. Okay, so the correlation, it'll, assuming that this line passes through B or close to B, it will, looks like it'll strengthen the correlation, mostly because the residual is smaller, and if it has a smaller residual than most of the other points, it'll make the correlation closer to 1 or -1, 1 in this case since it's positive. So correlation, and when I said the correlation will be greatly affected, I should have put closer, whoops, make it closer to 0. Okay, and then for point B, the correlation will not be greatly affected, but it'll make it, correlation will slightly sorry, I'm tired. Okay, correlation will get closer to 1, but just by a little bit. Get slightly closer to 1. Okay, the slope will stay the same and the y-intercept will stay the same, because this line, even though this is an outlier, if it follows the same trend, that won't affect the slope or the y-intercept. So slope and y-intercept. Basically unchanged, maybe a little bit. If this line doesn't pass through B, or maybe goes a little bit less than B, then it'll affect it a little bit more. So it remains basically the same. Okay, and then definitely the standard deviation of the residuals will decrease, because this residual is going to be smaller than the kind of typical residual of all these different residuals, right? Some of these residuals are kind of big. No matter what, even if this line is just a little bit like this, which it might be, this residual of B is going to be pretty small compared to the other residuals. So the standard deviation of the residuals will most likely decrease. Okay, and since you're estimating this line, right, we don't know for sure where this line is, it's such an estimation.
as long as you give a good reason, say, assuming that the line passes through B or gets closer to B, then kind of answer the question with that assumption. You'll get credit for that. So, but this one's very questionable, like a lot of these problems are. When you have to estimate, it ends up being questionable. Okay, for the second one, they say study of king penguins looked for a relationship between how deep the penguins dive to seek food and how long they stay underwater. Okay, for all but the shallowest dives, there's an association between x equals depth in meters and y equals dive duration in minutes that is different for each penguin. Okay, the study gives a scatter plot for one penguin titled The Relationship of Dive Duration Y to Depth X. The scatter plot shows an association that is positive, linear, and strong. Okay, so we just have to explain the meaning of that phrase, positive, linear, and strong, in different phases. Okay, so for A, kind of describing what the term positive association is in this context. So positive association in general is when one variable goes up, the other variable goes up. Or when one goes down, the other goes down. That's a positive association. They both do the same thing as far as increasing or decreasing. A negative relationship would be the opposite. When one goes up, the other goes down. Or when one goes down, the other goes up. So like they're doing opposite things. Okay, but in context for this one, you would say the greater, so we're looking at association between depth that the penguin dives and the duration of the dive. So you'll say the deeper that the penguin dives, the more time it spends diving. So underwater, spends underwater. Let's say. Okay, so that's meaning of the term positive association, so B. Explain the meaning of the term linear association. Okay, so linear association just means that, roughly speaking at least, the rate, so if you look at like the depth per minute, so like per minute of diving underwater. Here, sorry, let me think about a way to say this. Yeah, really, anytime you want to talk about a linear association, when you're really talking about something that has a constant slope, so you can kind of really talk about the slope. Say you can say like, and when you're talking about slope, you talk about every time the x increases by 1, the y increases by the slope. So you can say that for every increase in x by 1, so for every meter that the penguin dives, there's a constant amount of time that it stays underwater. So it just means, if they're, for every meter that they dive, maybe they're underwater for, 10 seconds, right? So every meter that it goes down, it's in the water for 10 seconds longer. So something like that. So okay, and yeah, so okay, so something like that. For for every meter that the penguin dives, it's underwater for some constant amount of time. Okay, part C, explain the meaning of the term strong association. Okay, so it just means that if you're looking at a scatter plot, they're talking about a scatter plot, that the lines or the actual points are close to the line of best fit. Line of best fit, or you could say the least squares regression line. Okay, part D. Okay, suppose the researchers reverse the variables using x equals dive duration and then y equals depth instead of the other way around. Would this change the correlation? Okay, for sure, no. Correlation never changes when variables are switched. Okay, and that should make sense because however they were correlated when you originally had the variables a certain way, when x was a certain thing and y was a certain thing, however they were correlated, to whatever extent they were correlated, even if you switch the x and y, it's still the same two variables, so they're still going to be correlated just as strong or as weak as before. This is an association between two variables, and the correlation just is what it is, whether you change the definition of, this one's x or that one's x. It shouldn't change the way that the two are associated to each other, correlated to each other. Okay, so that's correlation wouldn't change. The equation of the least squares regression line, you end up getting an inverse equation. So like, let's say originally you had equation y hat equals a plus bx. Then these would switch. This would be like x equals a plus b y hat. Okay, so yeah, so if you switch the variables, if you switch the variables when you do your analysis, find your least squares regression line. If you found the new least squares regression line after you switch the variables, then the variables would switch in the equation. So, and that would change the slope, and that would change the y-intercept. And just so you know, the slope would end up being the reciprocal, and the y-intercept would be something else. You could actually solve this for y. So by hat equals x minus a, subtract a from both sides, and then y hat would equal 1 over b times x minus a over b. Okay, so that would be the new y-intercept, negative a over b, and the new slope would be 1 over b. So both would change. Okay, so this next one, say stats teachers, cars. A random sample of AP statistics teachers was asked to report the age and years and mileage of their primary vehicles. Okay, here are a scatter plot, a residual plot, and other computer output, a computer output. Okay. So, so they, so here's the scatter plot, age and mileage, residual plot, age and residual, and then this computer output. Remember, right now for us, we're mostly just paying attention to coefficient, which is slope, coefficient, which is y-intercept, age, this is slope, and then here's r squared. Those are the kind of three things that we're paying attention to at this point in this class. Okay. So, is a linear model appropriate for these data? Okay, so when you're looking at if a linear model is appropriate, you look at three things. Look at the original scatter plot, so this line. So it looks like the data is pretty well, maybe except for that point and maybe that point. If those 2 points weren't there, this data would be very strongly correlated with this line of best fit, each other, but would be close to this line. And so these points are, even these points themselves are pretty close to this line. So, yes, and then this residual plot is pretty close, is pretty random, there's no clear pattern. There's a lot more residuals that are lower, but really that outlier is kind of affecting a lot of this stuff. So, yeah, but it looks like it's pretty appropriate based on that. And then the r squared, close enough to say it's appropriate. Close enough to 1, so. So A is linear appropriate would say yes. Remember, the most important thing is to deciding if a linear model is appropriate is if the residual plot doesn't have a clear pattern to it. So yes, because residual plot has no clear pattern. And then we'll just kind of mention r squared is, somewhat close to 1. And then we can even talk about the original scatter plot. Seems pretty linear. Okay, so part B, they say, what's the correlation between age and mileage? Interpret this value in context. Okay, so the r squared is really, that is a percent. I'm kind of do some scratch work. So r squared is really 0.837. So r is either plus or minus the square root of 0.837. Okay, we know it's going to be plus because we can see the slope from the scatter plot, that's positive. You can also see the slope in the computer readout is positive, and whatever the slope is, positive or negative, the r is the same, positive or negative. Also, we can just kind of think about the association from context. This is relating age and mileage. This is going to be a positively correlated association, right? When age goes up, mileage has to go up. There's no way age goes up and mileage goes down. It's actually not possible, right? So we know it's going to be a positive correlation, so that means r has to be positive. And if you take the square root, you get 0.915, and that's a positive 0.915. Okay, and then when you're interpreting this, you just say, so maybe there's like a strong or somewhat strong positive association between these two variables. So I don't have that much room to write, but you can read the answer key for some of these. So. Okay, so part C, they say give the equation of least squares regression line, identify any variables that you use. So for C, the equation is going to come from the computer readout. We know if it's for the least squares regression line, it's a predicting equation, so it's y hat. And then that's going to be the y-intercept. So the slope times x. And then will you say where x equals, was it just number of years owned? Okay. Just age of the car, and y is mileage. Age, y equals mileage. Okay, if I have more room, I really should kind of explain those better. You know, my age of the teacher's vehicle and y equals the mileage of the vehicle. So, okay, part D. One teacher reported that her 6-year-old car had 65,000 miles on it. Find and interpret this residual. Okay. So residual equals actual minus predicted. Okay, so we know the actual, that's what they give us, that's 65,000. Okay, then we'll do kind of scratch work. I'll do some scratch work up above. So if the, this is for a 6-year-old car. So let's see what the equation of this line would predict that the mileage would be if the age is 6, if x is 6. So just plug in, so y hat, I'll do it above, it's 3704 plus 8, and then plug in 6. I'm going to do that in my calculator. And you end up with 76,832. Okay, so we'll minus 6,832 that we found. Okay, and then we'll just subtract that in the calculator, and you get a residual of 11,832. Okay, and then when you're interpreting a residual, you really just kind of saying, you can use the word over and underestimate if you want. You can say that the least squares regression line overestimates. This is the predicted value, and this is the actual value. So the least squared regression line overestimates the mileage of a 6-year-old car. That would be kind of the nice, simplest way to say that. Okay, you should write that, but I'm running out of room, so. Okay, interpret the values of S and R. Okay. Oh my god. Okay, so this next one. So S, interpreting S, standard deviation. So actually here's the standard deviation. So we do have to pay attention to some other things sometimes. So standard deviation is up here in the computer readout. Okay, and you'll just say, I'm just going to say it instead of write it because I'm running out of room. You'll just say something about the mileage. So you're always talking about, when you're talking about standard deviation, we'll talk about it for the y values. So you're saying the mileage typically varies from 20,870.5 miles from the mean mileage for all cars owned by statistics teachers, something like that. And then the R squared, you can say something about how, the R squared here is 83.7%. So just say something about how 83.7% of the variable in the y value, which is mileage in this case, is explained by the linear relationship with x, which equals the age. So something like that. Okay, this is really the only problem that you are using your calculator a lot for. Actually using kind of the statistics features rather than just kind of doing calculations. the other problems. Okay, so this says late bloomers. Japanese cherry trees tend to blossom early when spring weather is warm. And later when spring weather is cool. Okay, here are some data on the average March temperatures in degrees Celsius and the day in April when the first cherry blossom appeared over a 24-year period. Okay, so we look at just each of these points. This is, for a certain year, let's say like this first point here, for a certain year, this means that April 14th was the first day in April that the cherry blossoms bloomed, and that temperature was 4 degrees Celsius that day. Okay, so just kind of, a lot of times just understanding what a single point means is helpful to understanding what this data represents in general. So, okay, for question A, okay, they say make a well-labeled scatter plot that's suitable for predicting when the cherry trees will blossom from the temperature. Which variable did you choose as the explanatory variable, and explain your reasoning? Okay. So I think it makes sense to use temperature for the explanatory variable. And then the response would be number of days in April. Until first blossom. Okay, and then explain your reasoning. Really, the reasoning would be it makes more sense that the temperature would affect the number, when the cherry blossoms bloomed, rather than the other way around. It's not like the cherry blossoms are kind of independently blooming on a certain day in April, and then that affects the temperature. So that doesn't seem likely. Okay, so for part B. Okay, and I should label, for part A, they say to make a well-labeled scatter plot. So, you should be making a scatter plot. I'm not going to do the whole thing. So well-labeled means the temperature in degrees Celsius should be labeled as the X, and then the days in April to first blossom. Okay, you should be able to read it, but I'm just kind of giving an example of what you should do. And then the other thing is to make sure you're thinking about the scaling. So you can see like the X values, they seem to all just go between the smallest is 3.2 or 1.5. It's a little outlier there, it looks like. And then the biggest X value is somewhere in the 6s. So maybe this goes from 0 to 7, So I would make this 0, and then just do 1, 2, 3, 4, 5, 6, 7. Okay, and then the Y scale, it looks like the smallest are there's a couple 3s, and then the biggest Y is 28. So maybe try to make this go from 0 to 30 maybe. So that's 0 here on the Y, and so maybe go by 5s. 5, 10, 15, 20, 25, 30, like that. Okay, and then now you can just plot all those points based on that scaling. Okay, so that's part B. That's part A, sorry. Scatter plot. Okay, so for part B, let's look at the calculator. So this Part B says use technology to calculate the correlation and the equation of least squares regression line. Interpret the slope and the y-intercept of the line in this setting. Okay, so let's go to the calculator. Okay, so first thing I already put the values. Go to stat and edit and put all the values in, which I already did. Okay, so next thing is to go back to stat and then go to calc, and we'll do number 8 for the len reg. Okay, so I've already got L1 and L2 in my X and Y list, so we want to store the regression line for later parts. Store it as Y1. Okay, and then we go down to calculate. You can just hit enter, you don't have to hit down. Okay, so that's our least squares regression line. So let's write that. Okay, maybe I'll round to the nearest hundredth, maybe, something like that. Okay, so we'll say it's y hat, predicted y is 33.12 plus or minus 4.69 x. Okay, so that's the least squares regression line. So interpreting the slope and the y-intercept, so the slope is this negative 4.69, so this is a negative relationship. So this is saying the colder the temperature, the fact that it's a negative slope, that means that the colder the temperature it is, the lower the temperature it is, the later day in April that the cherry blossom's first blossom is. Okay, so it's like when temperature goes down, days in April go up. So that's a negative relationship. Okay, and then specifically with this negative 4.69, it means for every x, the y decreases by 4.69. So in context, you'll say for each decrease in degrees Celsius, the days in April to first blossom decreases by 4.69 days. Okay, and the y-intercept is saying if the temperature is 0 degrees Celsius, then the day in April that to first blossom is the 33rd day. Okay, we know that there's not 33 days, but that's the interpretation. So. Okay, and really that would, I guess, relate to the next month in May, like the second or third day in May. Okay, so we'll say, let me see. Okay, yeah, so we'll say if the average temperature in these are average temperatures in March. I kind of didn't even really understand that until just now. Okay, if the average temperature in March is 0, and this makes more sense actually, is 0 degrees Celsius, the first blossom will be 33 days in April to first bloom, so that'll really be like May 2nd or 3rd. Wait, so there's March, April, so like 3 days, so May 3rd. First blossom will be on May 3rd. Okay, so that's interpreting the slope and the y-intercept. Okay, so for C, they say, suppose that the average March temperature this year was 8.2 degrees Celsius. Would you be willing to use the equation in part B to predict the date of first blossom? Explain your reasoning. Okay, so first off, that 8.2 is an x value, and it's much bigger than any of the other x values, right? The other biggest x values, I think, are 6.1 and 6.2, so much bigger than the other x values in the data. So it's that would be an extrapolation, and extrapolations are unreliable. So you would, when they say would you be willing to use the equation, so you'd probably not be willing to use the equation because you that extrapolation would be unreliable. So okay, part D, calculate and interpret the residual for the year when the average March temperature was 4.5. So now we'll go back to the calculator. So remember, we stored this regression equation here in the calculator. We stored this into y1, so this will be in y1. And we know that the actual temperature, so here, let's write this first. So for part C, so residual is actual minus predicted. Okay, so we know for if the average temperature in March is 4.5 degrees Celsius, we can find that in the table. So that's this point here. Okay, so if the average temperature is 4.5, that's the only point that has 4.5 is the x value. Then the days in April to first bloom is 10. So the actual y value is 10. For that x value, and then we'll use the least squared regression line. We'll plug in 4.5 into it, and that'll be our predicted, and then once we subtract them, that'll be the residual. Okay, so we'll go, we'll just look at y equals, make sure we see that that equation got put into y1 like we thought it would. Now let's do second mode to go to a blank screen, and then we're just going to we just want to plug in 4.5 into our regression equation. So we'll go to alpha and then trace. Oh, we'll do 10 minus. Yeah, so 10 minus to get the residual, and then we'll do alpha trace. Press 1 for y1, and then open parentheses so that we can plug in 4.5. So 10's the actual, and minusing the predicted. So I didn't even find the predicted. I kind of recorded this earlier. So the actual minus the predicted. I wish I would have found that, but actually let me see. So what is this part? Oh, this is really part D. What am I doing? Okay, so yeah, so the predicted is 12.015. Really, what am I doing? The actual is 10. The predicted actually must have been 12.035. Okay, and then we can see our residual is this, so negative 2.035. Okay. Okay, and then they say to interpret the residual. So we'll just say that the least squares regression line overestimated the days in April to first blossom for an average March temperature of 4.5. Okay, last one. Use technology to help construct a residual plot. Describe what you see. Okay, so let's go to the calculator. Okay, so we'll go to kind of the lists. So we'll do stat and edit.
Okay, so think about what we have here. So we want the first to get a list, one of the lists to be just residuals. So think about here, these are the actual y values. So next we're going to put in, make a list with the predicted y values. So we'll have actual and predicted, and then we'll subtract these two lists into another list to get the residuals. We'll do actual minus predicted, and that'll go into L4. Okay, so let's see how to do that. Okay, so next go into L3. And remember, our predicted values are going to come from that least squared regression line. So hit enter once you highlight L3. And then we're just going to do alpha trace F4 so that we can grab Y1. And then open parentheses. And we're going to plug in L1 into that. You know, L1 are the X values. So we're going to plug in all the X values, all these X values into the regression equation into Y1. And that gives us all these predicted y values for each x value. Okay, so that means now we're going to go to the next list and make this list L2 minus L3, which is actual minus predicted. So do second 2 to get L2, and then minus second 3 to get L3. You know, second numbers give you those lists. And that's it. So those are the residuals. Okay, and then now we want to plot those. So we want to take these, we want to take these x values and make the residuals the y values and make a scatter plot with those points. So with all the points where these are the x values and residual are the y values. So we want L1 to be the x list that we use and L4 to be the y list. Okay, so let's see. So first thing, you want to go to second y equals, which is stat plot. Yeah, so we use L1 and L4. Just kind of remember that. You can write it down also. Second y equals, hit enter. Okay, we want a scatter plot, so that's already highlighted. Make sure it's on, and we want to change this to L4. Okay, once you do that, you can just do zoom, and then 9 for zoom stat, and then it'll fit the data perfectly. And one thing, we don't want that line, so just unhighlight the equal sign associated with that line, and then just hit graph again. And so that'll give you the residual plot. Okay, and that's it, and then you can just kind of write that down. So describing what we see, I would say the residual plot shows definitely no clear pattern. There's no like U-shape either way. Yeah, it seems pretty random. It seems like just about an equal amount above and below. And yeah, it's just, I would just kind of focus on talking about the randomness and the lack of a pattern, which would indicate that this linear model is appropriate for this data. So, okay, 3.5, they say, what's my grade? Okay, Professor Friedman's economics course. The correlation between the students' total scores prior to the fall examination and their final exam scores is R equals 0.6. Okay, the pre-exam totals for all students in the course have a mean of 280 and a standard deviation of 30. And the final exam scores have a mean of 75 and a standard deviation of 8. Professor Friedman has lost Julie's final exam, but knows that her total before the exam was 300. Okay, he decides to predict her final exam score from her pre-exam total. Okay, first find the equation of the least squares regression line Professor Friedman should use to make this prediction. Okay, so when we have the data, then we'll do len reg a plus bx. Put the data into lists and then do len reg. Here we don't have the data, so things that we have here, and we'll collect these, write these on the side. So we have R, which is 0.6. We have the pre-exam mean, which is 280. And the pre-exam standard deviation, which is 30. And then we have the final exam mean, which is 75, and the final exam standard deviation, which is 8. So let's write all that down in symbols. So we know r equals 0.6. Okay, the pre-exam is definitely the x variable, the explanatory variable, and then the final exam is the response variable, the y. So definitely the pre-exam mean is going to be x bar. So that's 280. And then the pre-exam standard deviation, which is Sx, is going to be 30. Okay, and then that means that the y bar final exam mean is going to be 75. And then the final exam standard deviation is going to be 8. Okay, so for part A, and actually I'll put on the other side the formulas that we're going to use. So first off, for part A, say find the equation of least squares regression, line that you'd use to make the prediction. So we should use, y equals a plus bx. Okay, we'll always find b first for problems like this, where they give us the mean of the x's and y's and the standard deviations of the x and the y's. We'll find b first by using the formula r times, b equals r times standard deviation of y over standard deviation of x. Okay, we just look over here. Standard deviation of y is 0.6. And then times the correlation, r is 0.6. Standard deviation of y is 8, and standard deviation of x is 30, so this is 8 over 30. Okay, and then if you do that in a calculator, you get b equals 0.16. Okay, so that's our b value. Okay, now we'll use this, now we'll use this equation here to find A. So A is, is the mean of the y's minus b times the mean of the x's. Okay, they give us the mean of the y's on the left is 75. Plus the b that we just found, 0.16, times the mean of the x's, which is 280. Okay, so that means our A, simplify that in a calculator, and that's 30.2. Okay, so we go back, so now we know we've got our A value, and here's our B, and here's our A. And now we can just substitute it into our equation. Okay, so this is 30. Actually, let me rewrite this. Whoops. Okay, so our actual equation is y equals 30.2 plus 0.16x. Okay, so okay, for part B, they say use the least square regression line to predict Julie's final exam score. Okay, so they say her pre-exam score was 300, and that's an x value, so we'll plug in 300 into this. So her predicted y, her predicted final exam score will be this, with 300 plugged in for her pre-exam score. So in this case, for a 300-point pre-exam score, we simplify this. This ends up being 78.2 as a final exam score. Okay, for part C, they say explain the meaning of the phrase least squares in the context of this equation.
Okay, so I'm not going to write this down. I'll just kind of say it. So um, you can imagine this professor has a bunch of students. They all took the pre and post and pre-exam and the final exam. And so he took their pre-exam and final exam for each student and made a point. The pre-exam for a given student, the each point represents that student's pre-exam score, comma, their final exam score. That's the x and y of each point. There's their pre-exam and final exam scores. And then he plotted that on a scatter plot, or he could have, right? And he found a regression equation, a least squares regression equation. And that least squares, the term least squares regression equation, is the perfect equation that would minimize the sum of the squared residuals for any line that would go through the points in the scatter plot. For every line that you could draw that goes through the points in the scatter plot, you could calculate all the residuals for each point related to that line. You could square each residual and add it all together. And the line that we found is the line that minimizes that value of the sum of the squared residuals. So that's the meaning of the term least squares. Okay, so I'll just say that. You can kind of write that down whatever makes sense to you. Okay, so part D, Julie doesn't think this model accurately predicts how well she did on the final exam. Determine R squared. Use this result to argue that her actual score should have been much higher or much lower than the predicted value. Okay, so first we have R, 0.6. Okay, so if we square R, square both sides, then R squared is 0.6 squared, which is 0.36. So pretty low R squared, 0.36. So that means like not much of the variability. So there's variability with the Y values. Her predicted final exam score is not very correlated, right? Just 0.36 is R squared, so it's not highly correlated to her or really the students in this class, their final exam scores aren't highly correlated to their pre-exam scores. So that kind of supports her argument that her actual score could have been much higher or lower, could have just been different. Yeah, we don't know if hers would have been higher or lower just based on the correlation. We just have a good idea that there's a good chance that it could be different. So yeah, that's the kind of main idea. I'll let you read the answer keys for kind of more concise answers, I guess. Okay, so yeah, really the argument's going to be that the correlation is pretty weak. There's a pretty weak correlation between pre-exam and final exam scores. So using that equation, like the professor did, using that equation to predict her final exam scores, it's just not a good predictor. So, whoops, oh my God. Okay, this one's a quick one. So, calculating achievement. The principal of a high school read a study that reported a high correlation, right? Just a high correlation between the number of calculators owned by high school students and their math achievement. Okay, based on this study, he decides to buy each student at his school 2 calculators, hoping to improve their math achievement. Okay, explain the flaw in the principal's reasoning. Okay, so just because 2 things are correlated doesn't mean that one causes the other. So remember, I don't know if you remember in class, we looked at there was a website called Spurious Correlations, I think, and it related 2 things that are obviously not correlated. It showed graphically when you see them that they actually are correlated, or 2 things that are unrelated, like definitely one doesn't cause the other. We know that just because it's obvious by what they are, but they were correlated actually, according to the data. So the idea is that just because things are correlated doesn't mean that one causes the other. So, they say correlation doesn't cause or doesn't equal causation. And, it's just the idea that, there is a high correlation between number of calculators owned and their math achievement. But it could be, that, the more calculators that someone owns, maybe they own more calculators because they have more money, right? Makes sense. And if they have more money, they have money to hire tutors. And if they have money to hire tutors, then the students will do better in math class, So buying calculators wouldn't really have a big effect on students' math achievement, or probably shouldn't. It's really the tutors that have the big effect, or something like that maybe. But the main idea is that, correlation does not equal causation. Okay, so just kind of explain that however it makes sense to you. Okay, this last one in the review. Okay, so they talk about diamonds. Okay, so diamonds are expensive, especially big ones. To create a model to predict the price from size, the weight in carats, and price in dollars was recorded for each of 94 round, clear, internally flawless diamonds with excellent cuts. Okay, here's linear regression output for 3 different models along with a residual plot for each model. Okay, so this is going to be, we're going to use these different models to try to pick the best model or the one that has the best linear relationship. Okay. So they say model 1 is based on the original data, while models 2 and 3 involve transformations of the original data. And you can look at the way that these are highlighted, or these are described here. So model 1 is price versus weight, so that's just, X versus Y, really Y versus X. Yeah, really Y versus X. Price is Y, yeah. So this is like Y versus X. Okay, model 2 is ln of Y versus ln of X. Okay, and then model 3 is, this is a mistake. Okay, so this is a mistake in the way that they headed this. So you can see, this book made a mistake. This shouldn't be ln versus ln weight. This should just be versus weight. And you can even see down here they have weight as the way that they labeled the x-axis. Here they have ln of weight for model 2, and that's why they have ln weight as the transformed x value. Yeah, so here let's kind of correct this. So this should just be regular weight. So let's like cancel out that ln or cross out that ln. Okay, so this is ln of y versus x. Okay, so those are the 3 different models. Okay, and then remember, kind of for each model, if it's y versus x like in model 1, this would transform. This would just be linear, just as an original. There's no transformations here, so that's just kind of a linear model. If that model is linear, then y versus x then the data is linear. Here, if ln y versus ln x is linear, that means this
would relate to a power function. And then in model 3, if log y versus x is linear, that would support that the data is that an exponential model would be the most appropriate model to fit the original data. Okay, so here, let's answer this question. So they say, here's a linear regression model. Sorry, for part A, use each of the 3 models to predict the price of a diamond of this type that weighs 2 carats. Okay, so the weight is 2, so the x value is 2. So we'll say part A for x equals 2. And so now we'll use model 1 for model 1. So notice this is here I'll highlight. So this is this negative 98,666. That's the y-intercept, and this 105,932. That's the slope. So we'll say this is just y equals negative 98666 plus 5932 times x, but we know x is 2, so we can just plug that in. Okay, and we end up with 113,198. For model 1, so for model 2. Okay, model 2 is ln y versus ln x, so this will be ln y, the predicted, okay, equals, okay, so now we're going to use 9.7062 as the y-intercept and 2.2913 as the slope. Okay, so this will be 9.7062 plus 2.2913. Okay, but it's not x, it's ln x, so this will be ln 2 that we use. Because we're plugging in 2 for x, but the x in this case is really ln x. So, okay, so we can simplify this first to get what ln x equals. So if you simplify this, we get, or ln y, so we get ln y, the predicted, is 11.2944. Okay, and then remember how to solve. If you've got an ln y equals something, just make each of these left and right hand sides of this equation exponents of e, and then the e and the ln cancel, and you're just left with y hat equals e to the 11.2944, okay, which ends up being 80,370. Okay, so here, let me highlight these. That's model 1's predictor, that's model 2's predictor. Model 3. Okay, this is ln y versus x, so we'll start out the same way as the last one since ln y is the transformed y. Okay, we look at this model's y-intercept and slope, so 8.2709. Y-intercept plus the slope, 1.3791. Okay, and that's just actual x. Right, so that'll be 2. Okay, and then so that's what ln y equals. So that means that means our ln predicted ln y will
be, if we simplify that, that's 11.0291. Okay, and then that means that y hat equals e to the 11.0291, just like the last one, which equals 61,642. Okay, so that's what each model would predict the price would be of a diamond that weighs 2 carats. So each of those models predicts a pretty different price for a diamond that weighs 2 carats. So, okay, and then for part B, do that over to the left. They say, which model does the best job summarizing the relationship between weight and price, and explain your answer. Okay, so there's 3 things to look at. The scatter plot, if there's one given. Here there's not one given, so we won't look at that. So we don't have that. We'll look to see does the which one has the most random residual plot. So definitely, easily, model 2 has the most random residual plot. You can see model 1 has a definite curved pattern, like a parabola facing up. Model 3 has a curved pattern like a parabola facing down. Okay, so but model 2 has a very random residual plot. And then also the R squared value for the second model is by far closest to 1, 0.981, and this one's 0.873 and 0.873, both those. So yeah, so definitely no question model 2 is the best model. Because the residual plot is most random without any clear pattern, and the R squared is closest to 1. So, yeah. Okay, and we'll say, does the best job of summarizing the relationship weight and price of diamonds, because the residual plot for model 2 most random, without any clear pattern, like the other 2 models. And the R squared value for model 2 was closest to 1. Okay, so something like that. Okay, so that is everything.